And then this image gets projected onto this plane, and so forth. Well, if I unfold these objects, so here's this my plane here, right there. And here's the top. If the top is hinged to the front, just like a cardboard box, you hinge that to the front and fold him up, the top will sit right here. This is my front. If I hinge my right side to my front view, and this is a hinge, and he folds out, then that's my right side. If I hinge my left side to my front, and he folds this way, and that will give me a left side. If my rear is hinged to my left side here, then he folds on out also, and he'll sit right here. That will be my rear. And then if my bottom view down here is hinged to my front, then that folds down, and that gives me my bottom. So I get this arrangement of views. I get top, front, bottom, right side, front, left side, rear. They're in that arrangement. So I get this arrangement of views. The top sits directly above the front, right side adjacent to the front, so forth. This arrangement here of views, these are your orthographic views, but they're also known as third angle projection.
Oh.
What? They're known as third angle projection. What? What?
He broke out his camera.
It's known as orthographic projection. So, by using orthographic projection, where the sight of the person changes so that the line of sight is perpendicular to your plane, then you can project and get your 6 principal views of an object, which are your orthographic views. And the way they are arranged is known as third angle projection. So we do what's called third angle projection when we look at drawings. When you look at a blueprint and you see top, front, right side, and so forth, the way they are arranged is known as third angle projection. So we do third angle projection here. If I was overseas and we did drawings say, lived in Japan, you would do your drawing based on first angle projection. So in this case here, the front is always the same, but the bottom goes above the top, above the front, the top goes below. The right side goes here, left side here, rear there. So this is first angle projection. So if you read the views, you need to know whether you're looking at the views relative to first angle projection or third angle projection. So and it's how the views are arranged. The arrangement of views here are not the same as here. Here you say, okay, top sits above the front, bottom sits below the front. Here's reversed. Here the right side is on the right side, left side is on the left side. Here's reversed. The rear can go either way, but typically you'll see it in third angle projection, you'll see it hinged to the left. In first angle, you'll see it hinged to the left, but the views are reversed. So, typically, when you do metric drawings, you do first angle projection. But we don't deal with first angle projection here, so when we do metric drawings, we do third angle projection, and we have this little third angle projection symbol. It tells the person to read the views as if they're third angle, not first angle. Because metric implies first angle. Okay, so now these are your orthographic views. And in this example here, we took a box and we drew an isometric of it. So an isometric drawing simulates an isometric projection, where if you look at the initial view here, we're looking at it, so he's parallel to your plane of projection. So if I just looked at this, this would be my front view. But three-dimensionally, if I look at this, we have here, when we're dealing with this, we have an axis here. So we have a three-dimensional object. It has an axis here. We have the x-axis, the y-axis, and the z. So if we're looking at this, so this is parallel to our plane of projection, meaning our zx plane, then our object would sit like that. And then if our line of sight is there, then we'll look at this object and we would get an orthographic view of it. So, so we would get an orthographic view. But if we rotate this object so that a corner is facing us, then we pick up this edge. And so and then if we come here and rotate it along the next axis here, then these lines here, and it can be rotated at any angle, but when you rotate it at a specific angle, you do a 45 and you do a 35, 16, 26, 16 minutes, something like that. Then this line that was vertical is now coming out at you. So it's coming out at you. These lines that were horizontal appear to be going up at an angle. So if I do this with a three-dimensional object, then draw it, we're dealing with an orthographic projection. Which typically to do that, you have to do revolution. And revolutions are hard to do. The more complicated the object, the harder the revolution, because you're actually revolving the object. So to simulate what you get with isometric projection, you do an isometric drawing. So this is the edge here that you pick up when you rotate him, and then when you rotate him along your next axis, these lines appear to be going up at an angle. Well, we make that angle, depending on the rotation, that angle becomes 30 degrees, like that. So when I'm looking at this object here, that's my corner of it. This is a 30-degree angle, and then he's coming up 30 degrees, and then I get this isometric cube right there, based on this rotation. Right now the edge is vertical, but as soon as I rotate him like this, the edge, even though it's vertical, now it's coming out at you, but it still appears vertical. And these lines appear to go back at an angle. We make that angle 30 degrees, and we get an isometric. So it's easier to draw an isometric than to actually rotate this in 3 dimensions and draw a isometric projection. So that's your isometric. Well, your isometric has orthographic views associated with it. So we're looking at the front, right side, of course the left side is back there, top, the rear is back there, and the bottom is right there. So when we come here and take this isometric that we see, and we're looking along the orthographic views, we get this arrangement of views. Now, these 3 here are typically called your normal views. Only because that's based on your rules for orthographic selection of views. That's what you normally get, those 3. So they're called the normal views.
Is that understood throughout?
Yeah. So your task, course outline. What 3 problems in chapter 3 do you have? Or what? Okay. Okay, let's look at 316 as an example. Okay, so here's our isometric of this object here. So this is our common edge between our right side and our front view. And then this is represents our horizontal plane. So this is our 30-degree angle. He's going back 30. He's going back 30. We got that 30, 30. This is the edge, that common edge here, right there, between this front view and what we call the right side view there. So, now, when you look at an isometric, your isometric has isometric planes. Your isometric planes correspond to your orthographic views. Okay, so this plane right here is a right side orthographic plane. This plane right here is your front. Here's your top, and so forth. So again, if we just had a cube here, and we unfolded it, then we would get this arrangement. Wrong arrangement. We get the third angle projection arrangement, and then so when we fold this back up, this is an orthographic or a isometric plane. This is an isometric plane. This is your isometric plane. So I have my 6 principal views correspond to my isometric planes. My 6 principal views correspond to my isometric planes. So that whatever the true length and size of my ortho is, that's what it's going to be in my isometric. So any lines that it falls on the isometric plane like this, that's a true length line. So when I look at it orthographically, then whatever that is here, that length is the same length orthographically, or vice versa. So if I have an orthographic view, I construct an isometric drawing, then whatever the length is here is the true length here. Okay? Now, that only is true relative to lines that are on your isometric, orthographic, isometric planes, such that, and they correspond to your horizontal and vertical lines. So this object, when we draw this, this would be a horizontal line. When we draw this here, this would be a vertical line. So all my horizontal and vertical lines in my isometric are true length. So whatever the length is in the orthographic view, they'll be the same length here. Or whatever they are here, they'll be the same length here. It's just that my horizontal lines in my ISO is at 30 degrees. Here they're horizontal. So you have to know that. This here is true length because in my orthographic view, it would be part of my right side, and it would be a horizontal line, and it will be true length. Here, it will be true length here. Now, lines that are not horizontal or vertical are not true length, such as this angle. When I look at this from this view here, this angle here, however I want to do it, I can say this angle from here to here is not the same angle if I looked at it orthographically. So if I looked at this surface in the orthographic view, this angle here does not equal that angle there. Because this is revolved and this is looking at it head on. So you would get a different angle here. So if this said this was 45 and you tried to transfer that to here and then come down with a 45-degree angle, it will be wrong. Now, this is a true length line here. This is true length, this is true length. But that angle is not true length. I can't get the true length of that angle because it's rotated. But because I can determine an angle by other methods than just an angular value, so if I have this object here, I can say, okay, I can give you this distance right here and this angle, and I can do that orthographically. Or I can give you this distance here and this distance here, and that will control that angle. Or I can give you this distance here, vertical distance, and this horizontal distance, and that will control that angle as well.
But
So orthographically, I can control this angle this way, or this way. But when I transfer that to an isometric, I can only do this way or this way, because the angle looking at it orthographically is not going to be the same isometrically.
So from the front view, that angled surface would look flat.
Yeah, from the front, this will look flat.
Right.
But
Is there
from
a
the
way to convey that it is not necessarily part of it, or do you just assume that the line?
Oh, no. Yeah, we hadn't gotten to that yet. But let me finish this portion here to get the angle correct. So to get this angle correct here, whatever this distance is here, if I had this ISO, or whichever method you're going to use, that distance and this distance, then when I transfer that to my orthographic view, then I can say, I can take this distance here, come up that distance, and then we got, so that'll give us that. So that'll give us this edge right here. And we'll call him like that. So that's that edge right there. Well, the height of this is given, so the height of this is going to be whatever that distance is here. And that's at an angle, but when you're looking at it like so, it's this leg of my triangle. So when I'm looking at a triangle here, when I'm looking at it from this distance, I see this, I see that. When I look at it vertically, looking at it this way, I see that. The only way I see this true length here is to look at it in that direction perpendicular, then I see that distance there. So here I'm just looking at the side of this. So all I'm going to get is that height right there, which corresponds to that right there. So this surface, which you were talking about, this surface here is this surface laying back like that, and that's the height of that surface. So here's part of my front view is this right here, and that's what we got. Part of it, when I look in the front view, I see the surface, but the overall height of it is right there. Yeah. And we connect those two, and that's the height of this object. That gives me this height right here, and then that gives me this width right here. Now, any lines that are hidden by surfaces will show up as hidden lines in your orthographic views. So here we have a surface that intersects another, and when we have an intersection of lines like that, we pick up an edge. So that edge is either going to be visible, or if it's on the inside and it's hidden by material, then that edge is going to be hidden. So on the exterior angle here, we pick up, that's an angle right there, we get this angle, we pick up a visible edge. But on this interior angle here, we pick up a hidden edge. So that's the front view of this object. Yes, sir.
Do you need to do those lines, the hidden and the visible lines, in both the top, front, and rear?
Correct.
Okay.
Wherever, when you lay out your views, if your edges appear visible in a view, they should show up visible. If they appear hidden, they should show up hidden. Now, so if I were to fold this up, then my top would be directly above my front and be in line. So when I do my drawing, they should be directly above. My top should be directly above my front. So I use this as a guideline to bring him up, make sure it's lined up correctly. So when I'm looking in the top, these edges correspond to these edges right here. So this, where this intersects here, this is going to give me that top surface. This edge is visible. I get this portion of my surface here. Because of this angle, I pick up an edge here. Whatever that length is here, I can transfer that length here, and then draw my line. This surface here which looks this long from the side, is actually this edge of the surface. Again, we have that right there. So when I look down on top, that's what I see. I don't actually see this true length here. When I look in the front, that's what I see. But when I look in this direction, then I get the true length of that surface. So in the side view, I'll have the true length of this, but in the top, I'll have this edge of it, or this side, and in the front, I'm looking at that side. So this is that surface here, that's him there, and then we got the top that's there. Well, we pick up this outline right here as well, so there's going to be a cut in here, and that, whatever we do, that should match that, because that's where that edge came from. So if we say that's our cut, then we cut all the way back, there's material here, but there's no material here, so this edge goes away. So now we have the top view of this object right there. Now we have the top and the front. Now we got to do our right side view. Our right side view it has an overall height equal to this, and then we have the depth of it right here. So the height of it has to match this, and the depth of it would have to match that. So whatever this depth is here, that's going to be the same depth over here. So let's say that's our depth.
And that's where your true lines come in.
Correct. That's true length line. That's going to be true length line here. Okay, so here we pick up this edge, and now we see this edge on this surface, but we are looking from the right, we also see that edge, and we see that edge. So that looks like one continuous edge on the right side. But then we have a separation here where we have a cutout, so it produces those visible lines. And so that distance right here should correspond to that distance here. This distance here should be that distance from there to there. So when we're looking in the right side, we see this surface right here, which is that. We see this surface here, which is that. And then back here, there's a surface, which we see is that. And then we have our angle, our surface here. So he comes up, and whatever this distance is here, that locates this distance here. Whatever this distance is here, locates that. And then we just draw a line between the two, and that would give us our angle. So if we measure accurately, then the angle would be correct if we transferred it from the isometric to our orthographic view. So when we're looking through there, there's no material here, so this material is gone. So now we see this orthographic view of that right there. So now in this particular case here, we have a top, a front, a right side. There's no other hidden lines in this object. The only hidden line we picked up is here where this edge is hidden behind that surface right there. So you're going to take the isometric and lay out the orthographic views.
So we don't need to, do we need to actually draw the 3D?
You're going to have the 3D because it's right there in your book.
Right, but so we
You
don't
just
need
want
to
us
draw
to do-
that though. and-
No.
Okay.
You're taking that and laying out this right here.
Okay.
Just
From
the
that.
normal views or all six?
No, just the 3. We don't want to put too much pressure on you. Yeah.
Some of us want to
In
show
the book
off.
here, in the directions, it says to sketch all the views. Do you want us to sketch it, or do you want us to be accurate?
Oh, this is a sketch. So you have a grid. You have a grid on your drawing. I'm going to give you grid paper where for whatever number it's a 1-to-1. So for one grid here it corresponds to one grid on your grid paper. See how that works?
Yeah.
Yeah.
Now, if I had a hole in the object, because you do have a hole in that first object, let's say I had a hole sitting here. Well, orthographically, it's going to be round. Okay, so don't make it elliptical. But when you rotate it, it looks elliptical. Okay. Just like if you were to draw a circle on a sheet of paper, draw a circle, and it was actually round, and then you change the angle at which you looked at the circle, it would look elliptical. So as you change initially it'll be round. As you change the angle of the paper, it'll look more and more elliptical until all you can see is the edge of the paper. You can't see the circle anymore. So it will appear elliptical depending on the angle. So on these planes here, your planes right here, this would be a circle on this plane is an isometric ellipse. So on this plane and this plane, isometric ellipse, this and this, and that and that. If it's on a plane other than a isometric plane, then it's going to be an ellipse, but it's not called an isometric ellipse. If it's on the isometric plane, it's an isometric ellipse. Okay, so to get an isometric ellipse on a plane, let's say on the right side, if we just drew, then we locate the center of our ellipse or our circle. Whatever the diameter of our circle is here, so if we were taking this and putting it there, or taking this and putting it there, then you would have a grid here, and that grid would correspond to the diameter of the ellipse. So here it would be circular, but it would be equal to a true circle. And matching the grid up here, if this is 4 grids, say 2 grids square, then it will be 2 grids square here. So I can produce a square and then create a circle based on the size of that square. So if I had a square here and knew what, if I didn't know this, but I had my grid here, then I know that I have 2 grid squares here, and then that would just give me the diameter of my circle here. Now, same thing holds true here. If I knew what it is here, then I could transfer it here. So what I would do is, whatever this square is here, I would draw a square around the axis of my, around this axis, because it has an axis to locate the hole. So I transfer, that's the right side. Let me do a top. Let me do it in the top view. That way y'all see. So here's my top view. I locate the center of my hole, and then I would create a square equal to the diameter of my hole in that top view. And you have to orient it correctly. The problem is orientation. So if I orient it like this, the hole is not oriented correctly. It has to be oriented correctly. If I draw it like this, it's not oriented correctly. So this helps with the orientation of it. So once I locate this, produce a square, then I get that diagonal here and that diagonal there. The diagonal this is the longest distance there, so that would indicate that my ellipse would sit like that, right there. That's the correct angle of my ellipse. If I look at it from the right side, then this distance here is longer than this distance here, so that's my major axis of my ellipse. My ellipse would be oriented like so. It's not round, it's elliptical. So then if I come here, locate the center of my ellipse on this plane, create my box equal to the diameter of my circle, establish the longest end of the ellipse, then my ellipse will be oriented that way. That's how you orient your ellipse. So when you're looking at your drawing isometrically, In the top view, all of your ellipses, if it's on an isometric plane, should be oriented that way. So 313 shows you that, 318. But when I draw it here, it's going to be round.
Do we put hidden lines on the side view?
Now, if I had a hole in the object, now it produces hidden lines. So now I got a center line, so I'll show the center line of my hole. And then I got the hidden line, so let's say this is centered in there. Then I'll pick up a hidden line here for the diameter of my hole. I'll pick up a center line there to show the axis of my hole. I'll come here, pick up a hidden line here, and a hidden line here, and then the axis of my hole. Yeah.
I'm looking at the problem on 318. I mean, it shows a circle, and we could probably guess that's meant to be a hole in the object. How do you tell?
It's understood to go through unless otherwise indicated.
Okay, so if there was a divot, it would be.
If it didn't go through the part, well, in this case here, it doesn't give you the diameters and so forth. But if it had the dimensions on it, if it went through the part,
That's
then
what
it
I-
would just have a size.
Yeah.
If it didn't go through the part, should give you the depth of the hole.
So
And not-
anytime we see just a circle marked like that with a center mark, we should assume it goes all the way through.
Correct.
It's not a through hole like that.
Then it should
Yeah.
show you a depth.
A depth, yeah.
So all holes are assumed to go through unless a depth symbol is given to indicate the depth of the hole. So that's what your task is for the next 4 drawings.
Are we gonna get the 310?
Yeah.